Today on The Future of Everything, the future of AI and air traffic control. First of all, I want to say that we're still taping under Zoom conditions, so I apologize for any technical glitches. We're doing our best, and we hope you're all safe. Back to AI and air. There's a lot of talk about autonomous systems for transportation. There's driving cars, self-driving airplanes and helicopters, self-driving boats, self-driving spaceships. Each of these is an active area of research with critical considerations, I think, obviously, of safety and economy. Can we get people and cargo to where they're supposed to go safely and efficiently? They can have many challenges in order to be trustworthy and to be trusted by those who use them. AI algorithms, machine learning algorithms, show great promise in being able to assess the environment and make rapid conditions to control a vehicle. But of course, there's always worry about whether the AI will make good decisions in difficult circumstances, especially rare circumstances that the designers may not have anticipated or may have literally never happened before. Situations in which, of course, even humans can find themselves and which can be very difficult. But humans use their experience and judgment to make the best decisions, hopefully with good outcomes, but not always. How will AI systems make these decisions, and how will they stand up to the scrutiny if and when things go wrong? Well, Professor Mykel Kochenderfer is a professor of aeronautics and astronautics, as well as computer science at Stanford University. He is an expert at building autonomous systems, and in particular, systems for aviation. Mykel, what are the main challenges, as you see it, for trustworthy autonomous vehicles?
Okay, so I see there being two major challenges. The first one is, how do you build them in the first place? And there are a number of challenges associated with that. And then a second major aspect is, how do you then go about validating those systems?
Yes.
So going to the first part of how do you build these systems to be safe, it's actually really, really tough. And I don't think the general public appreciates how hard this is. It's hard for three reasons. The first reason is that many of these systems rely upon imperfect sensor systems that don't directly observe the true state of the world. So we see this with autonomous cars. So with autonomous cars, they rely upon vision sensors or LiDAR or radar. And many of these sensing modalities can be affected by occlusions, like a car blocking your vision of a pedestrian. There may be noise, there may be sensor failures, and so forth. And so making good inferences about what's actually happening can be very challenging.
Would you say in general that these imperfections in sensing are at the same level of human imperfections, or are they more or less or just different?
It depends upon the sensing modality. So like if we're talking about like radar sensors can see through clouds that they're often not impacted in the same way that pilot's eyes are affected. And so you can get superhuman performance in terms of along some dimensions, but sometimes not others.
Okay.
And a similar kind of challenge occurs when you try to apply these AI systems to medical decision making, which is more along your line of research, where we have to rely upon, maybe we don't call them sensors, but maybe we call them diagnostic tests. So we apply these different diagnostic tests, maybe for trying to determine whether someone is infected with the coronavirus or whatever. But there's a false positive, false negative rate, and so forth. And the sensors that we use for autonomy, for transportation systems, they are also impacted by false positives and false negatives. So for an example, we may think we see another aircraft, but it's not actually there, or vice versa.
Okay, so that's a first big challenge, is the imperfections in the sensing, which will be different from human sensing, but will still have its problems.
That's right. And so related to that is uncertainty in the future trajectory of reality. So
there's a lot of that, I notice.
there is a lot of that, especially right now, and our ability to model what's actually going on is a major challenge.
I believe a great baseball player once said, predictions are difficult, especially about the future.
Yeah, that's exactly right. And for many of the systems that we're interested in our lab, if you mess that up, the consequences can be fatal, right? So if we're trying to make a prediction about where another passenger aircraft is going to be over the next 40 seconds, I mean, most of the time they just fly straight, right? But sometimes they might turn left or turn right or start a climb or a descend, and we have to be robust to that variability.
So this is interesting because that implies that these systems not only need to sense the current present, they have to have some memory of the past, either recent or distant, and they need to have a model for the likely things that could happen, but I would guess also the unlikely things.
That's right. And many of the systems that we're interested in involve humans in the loop. And as you know, humans are a tremendous source of stochasticity or randomness in what happens. And so the pilots who are flying these aircraft, they may suddenly decide to maneuver to avoid collision, or maybe they're oblivious to how the situation is unfolding. But you make a good point that in order to make these predictions into the future, you have to keep track of what's happening in the past. And we see this come up quite a bit in automated driving. So for an example, if for the past 10 seconds or so, someone is coming up behind us and they're driving erratically, that will inform our predictions about what will happen in the future. And so we may want to be a bit more conservative as they pass us. But maybe we don't always want to be super conservative because that will be at odds with our efficiency.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Professor Mykel Kochenderfer about some of the challenges in building these autonomous systems for transportation. So I think we've gotten two so far. I'm pretty good. Yep. I think if I'm a good counter, we had sensor problems and we had prediction of the future problems.
Then another major challenge is the trade-off between safety and operational efficiency. And this is another aspect that people generally take for granted. They think, oh, well, let's just maximize safety, right? But if you're building an alerting system or a system that takes over and maneuvers for you, you can't tolerate too many false alerts, right? So if we're trying to build an aircraft collision avoidance system and it tells the pilots to take an extreme evasive maneuver, then maybe we can lower the collision probability, but it's not going to be useful at all. And getting that balance right is really tricky.
So, and I would guess that in those situations that it could be context specific in the sense that the most obvious example is your safety tolerances in an aircraft that is unpersoned, where there's nobody in might be different than one where there are 3 people sitting in or 400 people. So do we have to build kind of parameterized models where you can kind of dial up or dial down this trade-off? Because it really is a trade-off, and I guess you want to be able to have, I guess, humans make some judgments about that trade-off, or is that not the right approach?
Yeah, no, that's exactly the right approach. There's a lot involved in getting that right, though.
Yeah.
You're right. It depends upon
I made it like it was
situation.
One dial, and I guess that's unfair. I don't think there's just one dial.
Right. So at a high level, there's often a trade-off between safety and operational efficiency, but operational efficiency can encompass many different dimensions. So it could be measured in terms of number of false alerts. If we're building a system for cars, the number of hard brakes, and so forth. And so this is a very much a high dimensional space. And that is a major challenge for human designers. We like to think roughly in like 2 or 3D, but beyond that, it kind of boggles our minds. And so one of the research thrusts in our lab is figuring out how do you handle that dimensionality? How do you extract from a committee of humans how to make these trade-offs in a way that's sound?
Great. So this now, you've now put us into a deep hole of deep challenges, and yet we're not paralyzed. My understanding is that these systems are being built. What is the state? I don't know if you want to refer to general autonomous vehicles or concentrate on aircraft. What is the state of the science now? And what are some of the examples of new age technologies? I think that most of this was done purely by humans 40 or 50 years ago. And as a non-expert, I don't really have a sense of the pace at which things have been automated. So can you paint a picture for us about how things have been going and where they're going currently?
Yeah, so I'll focus on one particular application to aircraft collision avoidance, because that's what I've spent a number of years thinking about. The interest in aircraft collision avoidance dates back to the 1950s. There was the mid-air collision over the Grand Canyon in 1956 involving United Airlines and TWA, 128 fatalities. This led to the creation of the FAA in 1958, and a whole bunch of research on aircraft collision avoidance systems. It wasn't until the 1970s that the FAA actually established a program to create an aircraft collision avoidance system. And that system became called TCAS, the Traffic Alert and Collision Avoidance System.
Okay.
So if you might recall, computers back in the 1970s, they were not super advanced.
I'm afraid to say I do recall them.
So back then, memory was extremely expensive. The processors were very limited, and it placed a huge burden upon the human designers of the system at MIT Lincoln Laboratory, the MITRE Corporation, and other organizations in the 70s and 80s to anticipate the full spectrum of all the different situations that might occur. And what they had to do was encode what to do in every situation as a set of rules. Okay, and that's really complicated. That's super complicated.
And is limited by your imagination, literally.
That's right. So it turns out that I got to know a lot of the original engineers who worked on this program. Super brilliant people. And the system turned out to be a major success, but one of the challenges is anticipating and working with uncertainty. We as humans, we like to think roughly deterministically. If I do this, then that will happen. If I do that, then this will happen. But it turns out that in order to achieve the level of safety that's required of commercial air transport, this really requires reasoning about low probability events. And humans are just not good about thinking about events that may occur on the order of 10 to the minus 9 probability. And
1 in a billion.
1 in a billion. And that's where my research picked up. In 2007, what started out as equations on my whiteboard turned into a very large program called ACAS-X, the Airborne Collision Avoidance System X.
So it has a little phonetic relationship to its predecessor, the CAS.
That's right. The CAS, there's the connection there. Also, TCAS, the international standard was known as ACAS, and so this is a connection to that. The X just stands for extra cool.
Great. Before you tell us about it, let me just ask a very basic question about air traffic control. Is this collision avoidance part of the normal navigation system, or is it a separate system that recognizes that we're in big trouble and it kind of takes over? I don't have a clear model of whether this is a separate add-on or part and parcel of how a plane would do its entire flight plan.
That's a great question. So it's meant as the last safety net in a layered system of safety. And as you know, commercial air transport, it's unbelievably safe, right? And actually, as an aerospace professor and as a private pilot, third generation private pilot, it's just amazing to me that, you know, one of the safest places we can be is in a metal tube at 30,000 feet. That's just magic to me.
Yes.
But anyway, the reason why we have the safety level of safety in the airspace is because we do have strategic separation provided through, you know, there are different rules, like depending on whether you fly east or west, you fly at different altitude layers, there are different airways and so forth. We also have air traffic control. Air traffic control, they rely upon ground-based radars, and they call out traffic to the pilots, and they route the aircraft around each other.
Yes, yes.
So TCAS and now ACAS-X sits below that. So anything that's not resolved through air traffic control will be captured by TCAS and ACAS-X.
And this is present on the plane, not on the ground.
It sits on board the aircraft. It continuously monitors the aircraft around it, independent of air traffic control, independent of the ground-based radars. And so that level of independence is very important. And that's why when there are these aviation accidents, it's normally due to a failure of a number of different systems, because there's so much redundancy in the system as a whole.
Okay, so that was a big thank you. That was a very useful tutorial on the setting in which you found yourself, and I think you said in 2007, 2008 you started building this. Tell me how it was different and what challenges it exposed or solved. Right.
So it exposed a number of challenges. The approach that was taken, and although it came out of some research that I led, it eventually involved a number of people across a number of different organizations, and there are a number of technical aspects that we can talk about right now. But the success of this really was due to the leadership of a particular individual in the FAA, Neil Suki, who was willing to think outside of the box in terms of improving the safety of aviation. And I think as AI starts providing opportunities in other domains, we're also going to need that kind of leadership at places like the FDA and Department of Transportation and so forth. So what's different?
I'm going to interrupt. This is The Future of Everything. I'm Russ Altman, and we're going to return, I promise, with Professor Mykel Kochenderfer talking about the key elements of the new system for collision avoidance next on Sirius XM. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Mykel Kochenderfer about the new ACAS-X system he created starting in 2007 for collision avoidance. And then we'd like to understand, what were the good ideas, Mykel, in that system, and what did it teach us, and where does it leave us today?
Right, so one of the key ideas is to not have the humans try to anticipate the full spectrum of what might go on and encode rules for solving those issues. So what we do instead is we build models. So models that directly address those three major challenges. So we need a sensor model that captures all of the sensor error characteristics and so forth. We need a model of how the world evolves in response to the decisions of the system and the decisions of other humans and others in the system. And then another component is we need a way of encoding the objectives, right? Mm-hmm. So the AI system it needs to know what it needs to do, right? And it needs to be told it needs to be extremely safe, and it needs to try not to alert too often. There are other considerations as well, like for an example, you may not want to tell the pilots to climb and then all of a sudden tell them to descend, unless it's like super duper necessary. Right. So that's called a reversal.
I forgot to ask you, does this system ever take over the plane, or is it always advisory?
Great question. So it is advisory. However, some Airbus aircraft, like the Airbus A380, has an automated response to TCAS and in the future it will be automated to ACAS-X. But the pilot can always override it.
Okay, please continue. That's an important thing for us to know, whether it's a closed loop or an open system.
That's right. And so once we have those models, we need a way of optimizing the behavior of the system with respect to the objectives.
Right.
And we use a special type of optimization called dynamic programming. And dynamic programming, as a computer scientist, this is one of the most beautiful concepts of all time.
I must say it's also a core idea in computational biology, as you may know, in terms of comparing DNA sequences and whatnot.
So you have tasted of the magic. So yes. What's amazing with dynamic programming is that it takes something that seems to be computationally intractable and makes it tractable.
Yes.
So here's the computational challenge, right? So as I mentioned, we have to reason about the full spectrum of what might happen. And the space of possible, that there are more future trajectories than there are atoms in the universe. And then on top of that, we have to take into account their relative likelihood. And we have to reason about all of that. And it's just not feasible for every supercomputer to even enumerate all of the possible atoms of the universe.
And especially not within seconds, if that's what's required.
Right. So what we do here is we do all of the reasoning on the order of minutes offline, and we store that into a lookup table. And then that lookup table, that goes through an extremely rigorous verification and validation process. And then once that is certified, that then goes on board the fleet of aircraft, and then it just boils down to a lot of table lookups and interpolation. So much of the complexity is captured by this lookup table.
So two quick questions, and I have so many questions, but I think the first one is, when you were building models I know a little bit about model building, and in gross terms, one way is to do it with mathematical first principle models, and another way to do it is to inform it by data from many previous trajectories, many previous air flights. I'm wondering if you can tell me, are these the mathematical models, or are they data driven, or are they some sort of hybrid?
It's definitely a hybrid. It's a mixture of real data and human expert judgment.
Okay. So
for the system for manned aircraft, we collected a continuous stream of FAA and Department of Defense radar. That data informed a large dynamic Bayesian network that captured all of the statistical correlations and relationships between the relevant variables. This was done while I was at MIT Lincoln Laboratory. And then what we can do is sample from that model and then generate millions or billions of scenarios that we can then run in simulation.
Great. And if I can, my second question is, there are all kinds of airplanes. And so I assume like the sensors that are on the planes might be different. Certainly their flying capabilities. So I assume that there must be an element of the ACAS-X system that is aware of what kind of plane it's sitting on.
Yeah, there are different flavors. So there's one called ACAS-XA that's meant for large manned aircraft. There's XU for unmanned aircraft with different flight capabilities. There's one for small unmanned aircraft. And the challenge is that they all have different platform limitations, different sensing capabilities, and so forth. But returning to your question about the modeling, so we had a wealth of data for manned aircraft, but we want to put a flavor of this system on urban air mobility systems. Mm-hmm. So like personal air vehicles that are largely autonomous.
Yes. The Amazon delivery drones.
Or ones that actually carry humans.
Whoa, okay.
Yeah,
I'm not aware of my ability to order that from Amazon yet.
Yeah, that is not really available. Okay. But we need to build up models so that we can we can plan with respect
Support
to
it,
them,
yes.
validate it, and so forth. And so then there isn't a lot of data. And so we have to build tools that can help extract expert judgment about, the characteristics of these systems and how they'll encounter each other.
And so the next generation of ACAS-X, you might even rename it, will have a much broader range of applications, and therefore it will not just be informed by empirical data, but you will have to inform presumably with some sort of simulation, although you did mention expert opinion about how things, and so I guess this is an example where you're bringing in human expertise into this otherwise automated system.
That's right. So we want to bring in human expertise into the creation of these models, the validation of the models, but also in the specification of the objectives, right? And so for ACAS-X, this is one system to be used worldwide, right? And so there are many different stakeholders. We don't have to, it's not enough to just please the FAA. We need to make sure that Eurocontrol and the International Civil Aviation Organization, that they're on board with the system. And they have potentially differing objectives, different tolerances, different places where they want to be on the trade-off curves. And so we actually need AI to help arrive at consensus.
So as we finish up, we a couple minutes left. I wanted to go to this issue of validation. So you guys work very hard. You do your best effort. But even with your best effort and your, I'm sure, good relationships with all these agencies, they and the users need to trust these systems. How do you approach validation? Is it empirical? Are there things that are provable? What's the approach?
So the modeling and simulation, that gets us maybe about 70 or 80% of the way there. Other dimensions that have been important in establishing confidence in autonomous systems includes using as a basis fundamentally sound methods. So as you know, the dynamic programming has been around for a long time. The work of Richard Bellman in the 50s and so forth. These techniques are well established, yes. and they're sound. We also really want to the extent possible, come up with mathematical proofs that the system will be safe under certain situations. And our ability to do that depends upon what kind of system we're working on, whether it's an aircraft collision avoidance system or for driverless cars. In some situations, we may be able to provide proofs. Now, in order to prove anything, we generally have to make very strong assumptions about the sensor error characteristics and so forth, the acceleration limits, and but we have been working on tools, and people all around the world have been working on applying what are called formal methods to the verification and validation of these systems. Now, this becomes very tricky when the system involves a neural network. So a neural network is not being used in ACAS-X.
This is the new class of algorithm that has taken machine learning by storm. Which are famous for their good performance and for their inscrutability.
That's right. And also, over the past few years, neural networks have been observed to fail under somewhat benign examples. So if you make a small modification to a stop sign, maybe it misclassifies the stop sign as a yield sign or a speed limit sign or whatever. And so in collaboration with others, in particular Clark Barrett and Guy Katz, we've been looking at ways to prove properties about neural networks, and including situations where a neural network is being used as a controller. We have a long way to go until we're able to use these tools on very large networks, but we've been able to apply them to smaller networks as a proof of concept.
Well, this sounds extremely exciting, and obviously the validation aspects of all this is where the proof will be. But I want to thank you for your efforts in this area, and I want to thank you all for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.